afternoon. Today's lecture is about FIR filters. FIR filters. So today is an introduction course to FIR filters. So firstly, let's discuss what is a filter. A filter takes an input signal that is often got unwanted components such as noise. We input that into a filter, and the result is a cleaner version of that signal. And that is simply what a filter does. It removes unwanted components out of our dirty signal or our raw signal and converts into a nice clean signal for us to use. This signal can be used for data processing, maybe more filtering, whatever. So now, what materials are or what components do we need to make a filter? Well, filters can be electronic circuits. So electronic circuits could be mechanical devices, mechanical in nature, mechanical such as springs or sponge. They can all act as a filter. Got also acoustic ones, such as membranes used for mics. So, what is an FIR filter? Well, an FIR filter is computational. It's implemented in computer. Implemented in a computer. And that's the main point to understand. An FIR filter is implemented in digital circuitry such as a computer. Could also be a small microcontroller. Could be an FPGA. Could be an ASICs chip. Don't worry about what these are, they're not important. Could be anything that's digital in nature. Now, a major advantage of FIR filters or digital signal processing filters are they can be programmed, typically using, say, C++, assembly, Python, MATLAB, etc. That is a major advantage of being programmed because if you want to change your filter, you can now just reprogram the filter to do something else. However, if you have an electronic circuit or a mechanical device, that can only filter one thing and it can't be changed to do something else. You have to remake the entire circuitry or the entire mechanical device again. However, for digital signal processing filters like FIR filter, you can just change the code for it. Simple as. Now, the set of reasons why FIR specifically are better than other digital signal processing filters are they are easy to design, very, very easy to design. Easy to design. They have a linear phase response. And most importantly, they are stable. Now, these 2 points here about linear response, phase response, and stability, don't worry about that. That's explained throughout the lecture course. However, the easiest one to understand is that they are easy to design. Okay, now we've understood that, yeah, they're easy to design. So what actually is an FIR filter itself? So let me just get a pen. FIR. It stands for finite impulse response. Let's decode what that means. So an impulse response is when you put a sharp spike. So imagine in time you put a spike into, so that's an amplitude signal in time, into any system. Well, that is going to give you a impulse response in time. So if you put a spike into an electronic circuit as an electrical spike, you won't you won't get a spike out of it. You'd get something like this. And that is the impulse response. Don't expect to put the spike and then expect a spike out. Like that doesn't happen. You're going to get some weird graph like this. And that is called the impulse response. So that is your impulse response. Now your impulse response is infinite in time. It goes infinite in time. It just goes on forever and ever. Even though you might not notice it, it may become close to zero, may converge to zero, very close to zero. However, it does go on forever. Now this word finite. Finite means that, well, it shouldn't go forever. So to make it finite, you now put some window function, which basically limits in time. So this is all the impulse response you get. Now that doesn't really mean much to you. So let's explain that further. So FIR filters rely on impulse responses to do the filtering for us. So the impulse response is filtering for us. It's acting as our filter function. The finite part just limits how much of that impulse response is in time. So Maybe you have t equals 0 to t equals 2. Now, whatever that is, it doesn't matter. However, one thing we should understand is that a larger window just accepts more impulse response in time. Let's not get too complex or anything. Keep it basic for now. Finite cannot go on forever. Impulse response, just stick a spike into a system. The system gives you some weird response based on how it feels about that spike. And that's all you really need to know about FIR for FIR filters for now. So, what are the steps to making an FIR filter? Remember, we did say they are easy to design. So, how do you actually make one? So, steps to build FIR filter. So, step one, choose your parameters. Choose parameters. Do you want it to be a low pass filter, a high pass filter, a band pass filter, band stop filter? What frequency range? What's the cutoff frequency? So let's say, so the filter function, so function is like low pass, high pass, band pass, cutoff frequency, and any other parameters you could think of. There are quite a few parameters to look into. We'll stick to the basic ones, such as filter function. So is it a low pass, a high pass, and your cutoff frequency. 2. Choose the impulse response. So each filter function, low pass, high pass, band pass, they have their own individual impulse response. And they are simply just equations where you can stick the cutoff frequency into it. And that's why they're easy to design. It's just based on an impulse response equation, which is just there. Some mathematician in history calculated it for you. You can now just use it. So you have an impulse response. Step 3, choose a window function. Window function. Now, why do we have a window function? Well, a window function is there to make it finite. Remember, FIR filter stands for finite impulse response. We have our impulse response, which goes forever. Well, now the window function limits in time, hence making it finite. Okay, step 4, we multiply window function with impulse response. And that's how you actually make it finite. You just simply multiply the window with the impulse response. There are many types of window functions and they'll be explained throughout the course too. Okay, step 5. You just convolve the result of step 4 with input signal. That could be your sensor signal, could be anything you like. And that's the simple 5 steps to make an FIR filter. Now, as you increase the required parameters, so back to step 1, as parameters become more complex, you may have to add more steps to this list, but that will be also explained later, so don't worry about that too much. So what actually is the output of an FIR filter? So if you've come up with an FIR filter, if you made it, what's the end result? So end result is a bunch of filter coefficients. Remember in step 5, you said we convolve the results of step 4 with the input. Well, the output of step 4, which is window multiplied by impulse response, are some filter coefficients. They can be an plus 1, an plus 2, and go on for however long you wanted to go for. It's finite in nature, remember, so there's a limit to how many filter coefficients you can have. And then you just convolve with input. Convolve with input signal. And that will give you a filtered output. Now, throughout this lecture series, we will discuss everything from convolution, all the steps in more detail, how to choose parameters, how to choose cutoff frequencies, your window functions, your impulse response, and we'll look at more advanced parameters too throughout this lecture course. Thank you. Please like and subscribe.